Hello. It's been a long time since I've done one of these videos, but I'm now going to work my way through a few. I don't know how many I'll manage. A few exercises from Arthur Engel's book, Problem Solving Strategies, which I've made several videos from in the past. Um, I'm actually at the moment in the middle of a long sequence of, I think it's 172 exercises on number theory, which are mostly questions of divisibility. And I haven't made videos of the ones I've done so far because a lot of them were rather uninteresting, I felt, from the point of view of problem-solving strategies. You just did things like trying small modulus reductions and finding that the answer came out very quickly. But as I'm going through, I'm starting to find that I'm having to think a little bit harder about some of the questions. And so at this point, I think it seems like a good moment to record them, record myself solving some of them, although I think that there may be some that will be quick and not very interesting, but I think some of them, so far there haven't been any that have been interested me as nearly to the extent of the questions about invariance, which are in a different section on my YouTube channel. But nevertheless, I was talking to someone recently who said that actually maybe for some people it's actually quite helpful to watch someone else who has a different set of experience, just to see what's obvious to them and what's not obvious to them and that kind of thing. Sort of obvious things to think about. So even if a question seems a little bit disappointing to me, it may be that it doesn't to you, and there may be other questions that you would find, and I don't know who you are, but questions that you would find very easy, and you can watch me have a good laugh sort of watching me struggle over them. So let me see what the first of all, actually I need to share my screen. So is it gone? There we go. I also want to check that I'm still, I must still be recording, I think. Okay, so let's find the first one that I have not done. So it's number 48. This is chapter 6, if you're actually interested and have the book or something. So 48. Oh, let's make this pen a bit thicker. There we go. So find all integer solutions. I've done a couple of these, so some, and one or two of them I sort of afterwards felt I'd taken longer than I should have, because I was sort of expecting it to look like a certain sort of question, and it wasn't quite. So to A, x squared minus 3y squared equals 17. Now that looks as though it might actually require a bit of number theory, sort of genuine number theory, but I'm not sure. 2xy plus 3y squared equals 24. Okay, so this actually does look to me like something where I can't just look at it and instantly do it. So let's have a look at A first of all and see if there are any natural observations. So I'm going to look at parity first of all. So x squared and 3y squared have the same parity if and only if x and y have the same parity. So x and y must have different parities. So in other words, either x is odd and y is even or vice versa. So that's just looking mod 2. What else can we observe? So how about looking mod 3? So x squared will be 0 or 1, and 3y squared will be 0. Ah, so what's 17? 17 is minus 1 mod 3, so x squared minus 3y squared is congruent to 0 or 1 mod 3, and 17 is congruent to 2 mod 3, so no solutions. See, that's what I mean by a slightly disappointing question. I just hadn't really thought much. I just tried out mod 2. It didn't really, gave me a little bit of information, but didn't narrow things down all that much. Then mod 3 just completely killed the question. Perhaps I should have thought about mod 3, because I could see that that 3 would then lead to a quick simplification. What can I do about B? So I can certainly say that y must be even, because 2xy is even and 24 is even, and so 3y squared must be even, so y is even. So let's put that y equals, let's write it as 2u, and then rewrite the equation. So because I'm going to be able to divide through by something, so I'll get 4xu plus 12u squared equals 24. And let's divide through by 4, so we get xu plus 3u squared equals 6. And let's rewrite that as u times x plus 3u equals 6. So we're not going to have very many solutions, because the only integer factors of 6, the only way I can get integer factors of 6 are 1 and 6, 2 and 3, 3 and 2, 6 and 1, minus 1 and minus 6, etc., minus 2 and minus 3, and so on. So there's a finite number of pairs of simultaneous equations to solve, but I'd rather not have to do that. So let's just see if there's anything else we can say just to narrow down the number of simultaneous equations that need to be solved. So first of all, if u is positive, maybe I can't really narrow it down all that much. In fact, I can say the following: u, because whatever I choose for u, I can choose an x so that this bracket will equal 6 over u, as long as u is a factor of 6. So u equals minus 6, minus 3, minus 2, minus 1, 1, 2, 3, 4, 6, and x equals 6 over u minus 3u. And we wanted solutions in x and y, so all I have to do is double my u to give me y. So I could say y equals minus 12, minus 6, minus 4, minus 2, 2, 4, 6, or 12. And x equals 3 over y minus 6y. Is that right? No, the other way around. So so u equals y over 2. So it's 12 over y minus 3y over 2. Yeah. So we get the solutions like that. Let's move on to another question. I think that was fairly, in the end, fairly straightforward. Wasn't something like Pell's equation, or that's what I was worried about at first. So now I want 49. Find all the integer solutions of x squared plus xy plus y squared equals x squared y squared. And the other one, there's another one. X squared plus y squared plus z squared plus u squared equals 2xyzu. These are two separate questions. I'm not trying to find the solutions of these. So let's put 1 and 2. So let's do 1 first of all, or have a go at it. So I've done a few questions now where it's quite useful to do a factorization of, or a sort of factorization. So I'm going to bring the x squared and the y squared over to the right hand side. Then I'm going to add 1 to both sides, and then I'll get xy plus 1 equals x squared minus 1, y squared minus 1. So that's one observation. That's sometimes helpful. It's not absolutely immediately obvious how it's going to help here. So another possibility is just that this is done by means of an inequality. So I will observe that x squared plus xy plus y squared. Let's assume for a moment that they're not both 0. So obviously 0, 0 is a solution. So if they're not both 0, I better add that as, then I'll have that is strictly less than x plus y all squared. So to have a solution here, I need x plus y all squared is strictly greater than x squared y squared. Means that I need mod of x plus y to be strictly greater than xy. Let's just greater than mod xy. Let's assume they're positive. Oh, and by the way, if not one of them is not 0, then the other one's not 0, so strictly positive. So just to make things look nicer, so x plus y bigger than x times y. Well, we know that if x equals 1, then that holds, and if y equals 1, that holds. And if they're both at least 2, then this is at less than twice the max, or at most twice the max, whereas this is at least twice the max. So the only solutions to this are x equals 1 or y equals 1. So let's have a look at what happens if x equals 1. Do we get, so we have 1 plus y squared equals y squared. That would be if x equals 1, and we go back to the original equation. So that would tell us that y equals minus 1. Let's just quickly check. I'm claiming that x equals 1, y equals minus 1 as a solution. So I get 1, 2, 1, and 1. Yes, I do indeed get an answer. And obviously by symmetry, I'll also have, so I've got the following solutions: 0, 0, 1, minus 1, minus 1, and 1. And I know that if x and y are, yes, and that was necessary if x equals 1, that was the only solution to y. And if they're both at least 2, there's no solution. And indeed, we see that if x and y were not both positive, this is even less likely to, I mean, this is even less possible. Why do I say that, in fact? Oh, because actually, even if they're not greater than 0, we still need, let's go back to this. So if x and y are both negative, or if one of x is positive and the other is negative, we will still require that mod x plus mod y is greater than mod x times mod y, and that we have analyzed. And so I'm not going to check that very carefully. I'm pretty sure we've actually finished the problem. There's a little bit to check when it's negative, but not very difficult. So let's do x squared plus y squared plus z squared plus u squared equals 2x y z u. That's actually, I think I might just start by seeing if I can think of a solution. So if they're all 1 or something, then I don't have a solution. Yeah, so this is sort of interesting because when x, y, z, and u are big, then the right-hand side is bigger than the left-hand side, because multiplying four biggish numbers is going to be bigger than squaring the biggest of them. That's at least when they're big but of comparable size. But it's not absolutely obvious that, for example, if we took x to be big and y, z, and u to be all very small, or maybe x and y to be big and z and u to be small, it's not clear that we don't have a solution there. So actually, inequalities don't look as though they're going to be sufficient to produce an answer to this. So I think we need to look at mod considerations. So I'm tempted, because of the factor 2 there, to look at mod 2 and perhaps mod 4 as well, see what happens. So I know that because the right-hand side is even, I know that an even number of x, y, z, and w is even, as I can write down straight away, but that's not a huge constraint. It's very easy to satisfy. So what about mod 4? So we know that each of x squared, y squared, z squared, and u squared is either 0 mod 4 or 1 mod 4. This actually looks quite helpful, because supposing a single one of x, y, z, and u is even, then we know that the right-hand side is 0 mod 4. So I'll make it log x. So if x is even, then right-hand side is congruent to 0 mod 4. And the only way that can happen over here is if they're either all ones or all zeros, but they can't all be ones because x is even. We've got at least 1 0. So that implies y, z, and w even as well. So we've got a slightly stronger conclusion than the first one we wrote down. There we could have no even numbers, 2 even numbers, or 4 even numbers, but now actually we see that we must have either no even numbers or 4 even numbers. Let's see what happens if we have 4. See if we can sort of divide through by 2 or something. So let's have, if x equals 2a, y equals 2b, z equals 2c, and u equals 2d, then what does this equation become? It becomes 4a squared plus 4b squared plus 4c squared plus 4d squared equals 32abcd. And when I divide through, I'll get I'll get basically this, except x, y, z, and u replaced by a, b, c, d, and this 2 will be replaced by an 8. So let's just write that down. This is what we'll get. A squared plus b squared plus c squared plus d squared equals 8 a, b, c, d. So this is 0. So again, if one of those is even, they've all got to be even. If one of those is odd, then they've all got to be odd. And it'll be 1 mod 4. But that doesn't actually necessarily. The squares mod 8, let's just quickly think how they go when the numbers are odd. So 1 squared is 1, 3 squared is 1, 5 squared is 1, and that is actually quite useful. 7 squared is 1. So if A, B, C, and D are all odd, then over here we're going to get a number that's mod 4. Sorry, it's 4 mod 8. It's a multiple of 4, but not a multiple of 8. And over here we get a multiple of 8. So A, B, C, and D can't all be multiples. They can't all be odd, I mean. So they must all be even in that case, by the same sort of argument we've had before. So now we can divide them through by 2. And let's see what happens. So I think we're going to just get a similar thing, but with a. So if I divide them to it, I'm going to divide it by 2, but then still call them A, B, C, and D, because I'm running out of letters. So my new A is the old So this old a is the new 2a. So I will get 4a squared plus 4b squared plus 4c squared plus 4d squared equals 8 times 16, which is 128. So I get 32. Just a quick justification of that 32. It's because each of those I multiplied by 4, but the A, B, C, D I multiplied by a sort of 2 squared here and a 2 to the 4 here. So an extra 4. That extra 4 multiplied by 8 gives me 32. So one more check. So if A, B, C, and D are all odd, I'm not going to get that the square of every odd number mod 32 is 1. So what are the squares mod 32? And in particular, is it going to be obvious that I can't make 0 as a sum of 4? Oh, I can just look mod 8 still, of course. So I just multiply. If these are all odd, just looking mod 8, then I'm going to get 4 mod 8 here. And if they're all even, I can divide by 2 again, and this will multiply by 4. So what does the proof actually end up looking like? It'll be like this. I've got an argument that's going to go on forever and ever unless I actually say something slightly different. So I'm going to say let K be maximal such that 2 to the K divides A, B, C, and let's go back to the original letters actually just to avoid confusion. X, Y, Z, and U. So we write X equals 2 to the K A, Y equals 2 to the K B, Z equals 2 to the K C, and U equals 2 to the K D. And now I know that at least one of A, B, C, D is odd, otherwise I wouldn't have a maximal K. Observation number 1. And I also have observation 2 that 2 to the 2k times so x squared plus y squared plus z squared plus u squared equals, let's go back to remind ourselves what the original equation was, 2xyzu, and that's going to work out to say, when I divide through by 2 to the 2k, it'll be at a squared plus b squared plus c squared plus d squared equals 2 to the 2k plus 1 a, b, c, d. So I have a 2 to the 2k in front of all these and a 2 to the 4k plus 1 times a, b, c, d. I've divided through by 2 to the 2k. So looking mod 4, we know that this is because one of them is odd, we've got at least 1, 1, and we've always got either 1s or 0s, and that's certainly a multiple of 4. Just a moment. Why do I say it's just a multiple of 4? It's just a multiple of 4 as long as k is remotely big. We'll come back to that point in a moment. But I'll assume that k is greater than 0. So I haven't dealt with the case where they're all odd, but I think that will be. If they're all odd, we will have a problem mod 4 as well, because if x, y, z, and w are all odd, that's going to be 0 mod 4, and that's going to be 2 mod 4. So I can assume that. So that's not a hypothesis that I mean that's a thing I've now approved. K must be greater than 0. So mod 4, I get that's a multiple of 4, so that must be a multiple of 4. If I got at least 1, 1, all the rest must be 1. So A, B, C, D, all odd. and then mod 8, the left-hand side is now congruent. The 4 right-hand side is now congruent to 0, because I've got at least 2 to the 3. That's a contradiction. The only thing is I've made a hypothesis that I can actually have a maximal k. There's one situation in which there's no maximal k, and that's if x, y, z, and u are all 0. And that is indeed a solution to this original equation, and it's the only solution. So final answer, x equals y equals z equals w, equals u, I mean, equals 0. So that's sort of, yeah, you heard that one. The one sort of slightly interesting thing about this is that you sort of try, there's a little toolbox of things to throw at it. And typically, I think with these questions, some of them get you nowhere, don't really help, and then other ones do. And maybe with a bit more experience, one can sort of guess which of these, which mod is going to be a good one to reduce by, or whether it's going to be a mod thing, or whether actually you're going to have to use an inequality, and whether it's going to be a bit like this, where you look at the largest power or something. There are various different possibilities. One can usually narrow down fairly quickly which one is going to be the one that works. Okay, here's another one. Find all integral solutions of, let's have a nice, no, do it here. So this was question 50. X plus y equals x squared minus xy plus y squared. So I seem to quite like these symmetric polynomials. What can we do here? I don't see anything very obvious. If I take the xy over the other side, then I'll get x plus 1 using this factorization, x plus 1, y plus 1. So that gives me my xy plus x plus y, but it also gives me an extra 1. So it equals x squared plus y squared plus 1. It's not very obvious to me. What I should expect out of here. Should I resort to looking at parity in mod 3? I sort of feel it's oughtn't to be helpful. So what's my rough rule of thumb in a situation like this for saying that it won't necessarily be helpful? It's, and I think what I'm about to say may be incorrect, but let's just go for it. It's that no, sorry. What I was about to say was going to back up the opposite of what I want to say. So I feel the left-hand side can sometimes be bigger than the right-hand side. If x and y are very, wait a moment, is that true though? If x equals y plus 1, let's just try that actually. I just want to see how, I want to try to make this, oh no, wait a minute. So xy is going to be smaller than x squared plus y squared over 2. So broadly, this is going to be bigger than, yeah, this is going to be comparable to in magnitude to the largest of x squared and y squared, which is going to be significantly bigger than x plus y. So that's why an inequality feels as though it has a chance of doing something. And yet, down here, okay, so perhaps I could try rewriting this in terms of x plus 1, but is that going to look at all nice? Well, let me do that. I'm going to change variables. Feels as though it could be sort of helpful. So I get x plus 1 squared minus 2 x plus 1 plus 1 plus y plus 1 squared minus 2 y plus 1 plus 1 plus 1. So if I now just change x plus 1 to a and y plus 1 to b, I get ab equals a squared plus b squared is minus 2a plus b plus 3. Starting to get nastier rather than nicer, I think. Okay, I think back where I was before. I know that x minus y squared is greater than or equal to 0, which implies that x squared plus y squared is greater than or equal to 2xy, which implies that x squared minus xy plus y squared is greater than or equal to xy. So if this equation holds, it implies that x plus y is greater than or equal to xy. And now we're back to on familiar ground. We know that x or y must equal 1, because if they're both at least 2, then the product is going to be, or they can both be 2. So let's check whether 2 works. So 2 plus 2 is 4, and here we get 4 minus 4 plus 4. So x equals y equals 2 is a solution. If x equals 1, then we get, well, let's make y equal 1. Then we'll get x plus 1 equals x squared minus x plus 1. So we get that x, or 2x equals x squared, which tells us x equals 0 or x equals 2. And we've done the case x equals 2. That'll, oh no, so that was if y equals 1. So is that the case then? If x equals 2 and y equals 1, I'll get 3 here. And here I'll get 4 minus 2 plus 1. So x equals 2, y equals 1. By symmetry, y equals 2, x equals 1. And x equals y equals 0 is clearly a solution as well. I think I won't check. I'm fairly sure I've just ruled out all the other possibilities there. So I went down a little bit of a red herring, sort of wrong path here, but eventually recovered, or sort of my sanity was regained. I realized that this was a sort of basic AM-GM inequality type problem. So now we've got one that is not finding all integral solutions of something. So that's going to be interesting. It's a totally different type of question. So 51, let P equal P1 times Pn, where n is greater than 1, strictly greater than 1, be the product of the first n primes show that P minus 1 and P plus 1 are not squares. That's nice. And maybe it's nice. And this looks very much to me like a small modulus type thing. We don't really know of any properties that stop something being a square, say I, other than not being a quadratic residue to some appropriate modulus. So what do we know about P? We know that P is going to be an even number. So P minus 1 and P plus 1 are odd, which does not rule out there being squares. So mod 2 doesn't seem to be very helpful. In fact, mod any prime number doesn't look super helpful, because say I take mod 17 or something, then I know that P is a multiple of 17, so P plus 1 is 1 mod 17, and since 1 is a quadratic residue mod 17, and indeed mod any prime, then that doesn't rule out its being a square, although perhaps if we look. So I feel as though maybe we want to look mod P squared, or perhaps mod 6 or something like that. So let's think about that. Yes, now mod 6 is not going to be very useful because it's still going to be 1 mod 6. So I think looking at mod P squared, so perhaps mod 4 will be helpful. So P is 2 mod 4, and so P plus 1 is not a square because it's 3 mod 4, but P minus 1 perfectly well could be a square. So what I'm actually looking for is I want to find, I would like some prime Q such that Q plus 1 and Q minus 1 are not squares. This is a stronger thing to ask for, but it's my sort of hoped for strategy. Are not squares mod Q squared. Because, oh no, wait a minute, that's not quite right, such that AQ plus 1 and AQ minus 1 are not squares mod Q squared if Q does not divide A, because something I know about P, once n is big enough, but I don't get to assume that n is big enough. I might have to do something separate for very small primes P. What happens if I take 25? So I want to know whether, no, let's go for 9. Why go for 25? So 9. So what I would ideally like is that 2, 4, 5, and 7 are not squares mod 9, but I think that's going to be just false. Let's have a look. 1 squared is 1, 2 squared is 4 mod 9. So it's hopeless to hope for 4 not to be a quadratic residue mod 9. Yeah. So 9 doesn't work, and it's starting to look a bit optimistic to think that anything could work. For example, if I look at take Q equals 5, then I'm going to have 4 being a square. Q is 7. So could I be really lucky? 6, 8. So all the numbers that are 1 less than or 1 more than a multiple of 7 that isn't a multiple of 49. So 6, 8, and 14 will get 13, 15. 21 will be 20, 22. 28 will be 27, 29. And 35 be 34 and 36, which is not good news. And that was possibly slightly interesting. There's some reason that I got 36. There wasn't there? Because if I take q minus 1, q minus 2 times q plus 1 is equals q squared minus 2q plus 1 equals q minus 1 squared. So this strategy is guaranteed to fail. So where are we going to be able to prove that they're not squares? Let me so although I feel as though I've managed to rule out this having any chance of working, let's just at least see what we can say. About what P is mod various small primes. So or there's one other prime that I've not looked at, which is maybe this is this is such a nice question. So look, I was going to say the prime that I've not looked at is Pn itself. Could that be significant? So I have that P is a multiple of Pn, and it's not a multiple of Pn squared. It's also, for what it's worth, an even multiple of Pn, but that doesn't feel as though that should be significant because product of P1 up to Pn minus 1 is just going to be some, who knows what it'll be, mod Pn. So where am I? The thing is, there are so many quadratic residues around that it seems rather unlikely that they would all be avoided. Unless we can somehow prove something funny happens. So let's have a look at some of these numbers. I'm just going to look at their prime factorizations because I'm getting slightly desperate. So n is greater than 1. That was a start, actually. So 2 times 3 equals 6, and then the two numbers are 5 and 7. And then 2 times 3 times 5, I'll call it P. I'll call it capital P 3, i.e. the product of the first 3 primes. That's 2 times 3 times 5 is 30. I have 29 and 31. So so far they're all primes, which is not hugely helpful. I lost my internet connection just then, so I'm not quite sure what's happened. May have to splice some things together, but let me reshare my screen. So I hope that this will still be just part of the same video, but otherwise that'd be a bit of a jump. Okay, so where was I? I was writing P3 for the product of the first 3 primes and so on, and just having a look at what some of the first few products and their plus or minus ones actually are, to see if I can, I think it's sort of useful to do this just to rule out possible ideas for proofs. For example, I'm already getting the idea that showing that some prime divides this number, but its square does not divide that number. Oh, actually, come to think of it, that's given me a little thought. So I've got sort of large primes dividing this number, but their squares don't, and they sort of can't because they're not big enough. So perhaps there's something. No, I don't think that's going to help. So P4 is, I multiplied, this was multiplied by 5, so now I have to multiply by 7, I get 210. So I have the numbers 209 and 211. 209 looks as though it's a multiple of 11 by the normal test for divisibility by 11, and indeed if I add 11 to it, I get 220. So let me just write that as 11 times 19. And 211 multiple of 13. I very much doubt it. If I add 39 to it, I get 250, not 260. And 17 squared is too big. So that's a prime. But it's not quite clear what I can reduce it. So if I look at, say, the reduction mod 7 of this number, I'll get 4 times 5, which is 20, which is minus 1. And if I look at the reduction, so this will be plus 1. This is plus 1 mod 7. That simply doesn't rule out. But if I wanted to reduce mod 49, then I get 196. So that would be plus another 15. That's congruent to 15 mod 49. So can we look mod p squared? I mean, mod the biggest prime that divides it. Or can we do something else a little bit? There's some trick I should be thinking of. I'm not thought of. So one thing I do know about p minus 1 and p plus 1 is that they are not divisible by any prime from any of the first n primes. So what? So if they were squares, they would have to be a product of squares of primes, all of which would have to be bigger than Pn. But it's such a big number, P1 up to Pn, multiplied together, that I don't really see why that's not, why that should be expected to be all that difficult. What other properties do primes have to say? Rather, what other properties do squares have? If p plus 1 is a square, then p is a product of two numbers that are 2 apart. That, unfortunately, I don't see any reason for that not to be the case. Oh, or do I? Wait a moment. Right, that's booking mod 4. So p plus 1 is a square, then p is congruent to, so if p is, oh, well, we know that p is even. What was I trying to say? Then p plus 1 is congruent to 1 mod 4, because we know that p is even because it's divisible by 2. So p plus 1 is congruent to 1 mod 4. Because p is even, so p plus 1 is odd. The only odd squares are ones that are congruent to 1 mod 4. So that implies p is divisible by 4. But we know it's not divisible by 4. So we've actually ruled out p plus 1 being a square. That was very quick. I mean, not quick in total, but quick just then. So if p, let's try what happens here. So if p minus 1 is a square, then p is congruent to, again, p is even. So, but just a moment. P is a multiple of 3. Then 2 is quadratic residue mod 3, but it's not a quadratic residue mod 3. Really quite confused there because I thought I'd ruled out mod 3 and mod 4 telling us anything useful, and now suddenly it seems to have told me something useful. So let's go back and have a quick sort of look at this again. So I know that p is a multiple of 3, as long as n is big enough. So p minus 1 is 2 mod 3 and 2, so it can't be a square. And then I know that p is 2 mod 4. Okay, I feel very annoyed with myself that that took so long. I was trying to be much too clever, and somehow my mistake there was to rule out various methods, but rule them out wrongly because they were perfectly decent methods in the end. All right. Oh, here's a very a nicely different looking question. 51. A1, A2 plus A2, A3 plus AN minus 1, AN plus AN A1 is equal to 0 with AI belonging to minus 1, 1 for each I presume that means. Show that 4 divides n. I feel this should be fairly easy, but why? Let me just write that a bit more clearly. That says AN is A1. So I sort of go around the cycle multiplying things together. Well, certainly n must be even. Why? Because the sum of all these numbers is even. Each number is plus or minus 1, so it's odd. And so we have to have an even number of odd numbers to make an even number. So n must be even. So we just want to strengthen that. How do we get beyond n being even? So So notice n doesn't equal 2 since a1, a2 plus a2, a1 is either -1, sorry, -2 or 2, which is not 0. So I'm guessing that it's always the case that this number is congruent to n mod 4. That would be a nice little hypothesis that's consistent with what I've got so far. And indeed, if n equals 1, I get that a1, a2 is 1. But if n is 2, I've got that it must be 2 mod 4. Let's just check if n equals 3, just to see whether this conjecture is, if this conjecture has legs. So a1, a2 plus a2, a3 plus a3, a1. Must that always be congruent to 3 mod 4? I can see that this is not going to be true, because if I write it like this, a1 times a2 plus a3 plus a2, a3, then I see that I can choose a2 and a3, let's say a2 equals a3 equals 1. So then I get a 1 here and I get a 2 here. Now I can choose a1 in 2 different ways, and I can choose either 1 or -1, and I'll get 2 different answers, mod 3. So that doesn't work, but perhaps it works. Perhaps we can at least show, so that rather strong conjecture is incorrect, but could we show, for example, that n congruent to 2 mod 4 implies that this, well, let's call it left, just implies that the left-hand side is congruent to 2 mod 4. That seems like a reasonable conjecture, that it's the mod 4 problem that gets in the way. Well, we got somewhere by looking at this factorization, so why don't we do something like that and say, I'll write it as a2 times a1 plus a3 plus a4 times a3 plus a5. This is looking very promising, I think. Or is it a6 times a5 plus a7 plus, let's suppose n, I'm assuming that n is even, because we know that n must be even, so let's have n equals 2m. So I'll get up to a 2m times a 2m minus 1 plus a1. And each of these numbers is 0, 2, or -2. And each of these numbers is 1 or -1. Mod 4, there's no distinction between 2 and -2. That's quite nice. So this will give me 2 mod 4 whenever ai and ai plus 2 are the same. When I've got 2 consecutive odd ai's that are the same, then I'll be contributing 2 mod 4 to the sum. When they're different, I'll be contributing nothing to the sum. So I want to know how many times will it be the same and how many times will it be different when I run through a whole bunch of 1s and -1s. Well, I know that if I've got, so I've got a sequence of 1s and -1s. And I know that the total number of changes when I get right back to 1 has to be even. So the total number of so the total number of times when it adds up to 0, so when they're different, it adds up to 0. So the number of times it adds up to 0, it's got to be even. The number of times it adds up to 2 mod 4 is going to be m minus an even number, which if m is 2 mod 4 will be an odd number, and that I think does it. So if m is even, then, well, first of all, actually, before I start that, before I split into cases, I say an even number of a 2r minus 1 plus a 2r plus 1, so these things in brackets here are 0. So if m is congruent to 0 mod 4, then the sum was an even number are 2 mod 4, and if m is congruent to 2 mod 4, then an odd number are 2 mod 4. So LHS is congruent to I mean m being 0 mod 4, I meant if m is even, n is 0 mod 4, so if m is even, and if m is odd, then odd. So I'll just write it more clearly by just putting even, odd, then an even or odd. So the left-hand side is congruent to 2m mod 4. And so we get that n must be a multiple of 4. That was quite nice. And at the moment, I'm quite interested in the problem-solving process and just these little experiments that go on in order to just look at a few small things, learn from them, and guess what the proof is going to look like, and then eventually go back and improve it based on little observations on small examples. And I find that process really quite interesting, and I want to understand it better. I've got time for one more, I think. This one looks not so difficult. Oh, maybe famous last words. So 53, 3 brothers inherit gold pieces. This looks actually really quite dull, sorry about this one. Weighing 1, 2, up to n. For what n can be, oh wait a minute, is it more interesting than I thought? Sorry. For what n, I'm not sure I have got time for this. Can they be split into 3 equal heaps? Sorry, the reason I thought it was boring was that at first I thought it was just, is the sum of the first n integers a multiple of 3 or not? That would be boring. I just reduce mod 3 and see what happens. But of course, that's not enough to be able to guarantee that we can split them into 3 equal heaps. For example, if we have just 1, 2, and 3, we can't split those into 3 equal heaps, even though the sum of 1, 2, and 3 is a multiple of 3. But it is a necessary condition because coins have integer things. So let's at least work out what happens when you take the sum of the integers. We get 1, and then 1 plus 2 is 3, and So that's 0, and you get 0 and 0, and then 1 and 0 and 0. So we certainly have a necessary condition. N is congruent to 2 or 0 mod 3, but that's not necessarily a sufficient condition. Maybe it will turn out that it is a sufficient condition as long as n is not tiny like that. So I'm going to try a little experiment. 1, 2, 3, 4, 5, 6. When I do it then, I could put 6 and 1 together, 2 and 5 together, and 3 and 4 together. So that looks pretty simple. But that's not necessarily going to work if I have 9 coins. So and actually that was just I also should have considered the case 1, 2, 3, 4, 5 as well, actually, because that adds up to 15. If I want 3 things of 5, I'll have to have a 5, and then a 4 and a 1, and a 2 and a 3. So that actually works as well. So far I can do it for 5 and 6. I can't do it for 2, and I can't do it for 3. I think I'm going to have to carry on with these experiments because, for example, this one took me by surprise a little bit. I was expecting it not to be possible, and then it turned out to be quite easy. So let us jump ahead. We can't go for 7 because that's so for 8. So the sum of the first 8 integers is 36. So I need to split them up into sets of size 12. Oof. But that looks kind of easy as well. So I could put 8 with 4, 7 with 5, and then all the rest. Once I've got 2 of them, I've got the third one. So that's actually an interesting observation as well. So 8 was all right. So 9, I won't do too many more of these because I haven't got very much time. I've got. So now they've got to add up to 45. So each got to put them into groups of 15. So I can do 9 and 6, and then 8 and 7, and then the rest must work. So 9 worked. So I really do believe now that the right condition is that n is congruent to 2 or 0 mod 3, but is not equal to 2 or 3. Full stop. I think apart from 2 and 3. So let me see what I would have to do to prove that. So now I've got 1, 2, up to n. And I know that this lot adds up to a multiple of 3. So now I want so all I have to do is prove that I can get 2 of the 3 numbers, and then I get the third one for free. That's something I've just been observing. But how do I make sure I can get 2 of the numbers in a really systematic way? That's because it was all very well when I could do it with just a sum of 2 things, but when n gets big enough, 2 numbers is not going to be enough for me to produce a third of the total. So I'll have to start having larger sums, but it looks as though it ought to be pretty easy because is there a more sort of, that was one way of doing it, but is it the only way of doing it? So 15, I could have taken the outer 2 and the middle one. No, that wouldn't have been nice. So here's a suggestion for an algorithm, but it's going to be a little bit tedious to prove that it works. Is I'll take the largest number I can, then the next largest number, then the next largest number, and so on, until I spill over. And when I spill over, I'll just take the largest one that I can that gets me the total. And then I'll do the same thing Let me just illustrate this actually, because I don't think I'm explaining myself very well. Let me write the numbers. I'll do it for 11, for example. So I'll write them backwards. 11, 10, 9, 8, 7, 6, 5, 3, 2, 1. So I'm just trying to find a reasonably systematic way of getting my things. So what's it have to add up to? 11 times 12 divided by 2 would be 66. So I've got to get them to add up to 22. So what I'll do is I'll go 11. I'll be very greedy about it. So 11, then the next one will be 10. And now I'm nearly at 22. But so I'll have to take a 1 here. There we go. And having done that, that's my first group. I'll go for 9, 8. So I've got up to 17. I can't add 7 or I'll spill over. But I can go for 5. And now I've got 22, and then the rest. That's my proposed algorithm. Could it go horribly wrong? So if I have a general n, I will take n minus 1 down to n minus some r, and then I'll take a final s. So this r and s, so this is the r is the last point at which I am, so it's the first point at which if I then chose n minus r plus 1, sorry, n minus r minus 1, I would get bigger than the number I'm aiming for. So instead of choosing that, either I've reached the number I was aiming for, or I have whatever, s will be the difference between what I've got so far and the number I'm aiming for. So then the next one will be n minus r minus 1. I'll keep going. So what I don't actually see is why I might not find that, for example, s might be 1 here. I might just get myself 1 less than a multiple of than the number I was aiming for. And I might also find when I use this that just at the point at which I stop, I'm 1 less, but unfortunately 1 has been taken. I don't see how to rule that out. So that particular method for doing the splitting, actually I've got one little observation, which is that if n is a multiple of 6, then I'm okay, because I can do, and I think, oh no, I think this is going to be helpful. So I could do 11, I can do n together with n minus 5, n minus 1 together with n minus 4, and n minus 2 together with n minus 3. So I can have little sort of groups of 6. And in fact, that will tell me that I can do it if n is congruent to 0 mod 6. But it also tells me if I get down to a group of, actually I'm done now. If I get down to something that's got 5 things in it, then I'm okay. And if I get down to something that's got 9 things in it, then I'm okay. So in other words, what I can do is I can remove the top 6 things and spread those out into equal piles. So that proves that if I can do n minus 6, then I can do n. And since I can do 5 and I can do 6, and then I can do everything that's 5 or 6. Oh, I can do 5 and 6 and 8 and 9. Then when I remove, if I start with something that's 2 or 3 mod 6, I can get it down to 5, 6, 8, or 9. And that's what I wanted. I don't expect to be able to do it when it's 2 or 3. So I have managed to prove that the condition is n is congruent to 2 or 0 mod 3, and either n equals 0, which is a boring trivial case, or n is greater than 3. And there I must stop. So let me, I haven't done this for so long that I have forgotten how to stop the recording, but yes, I'm